Have you ever wondered why some materials bend while others break? Or how engineers know what materials to choose for structures, machines, or even medical implants? In this video, we're diving into the mechanical behavior of materials, how materials respond to forces and the environment around them. We'll start by walking through a typical tensile test setup, one of the most common ways to understand how a material stretches, deforms, and ultimately fails. From that test, we'll extract the stress-strain relationship, a powerful tool that reveals key properties like the Young's modulus, yield strength, and toughness. Then we'll break down the four fundamental types of loading: axial, transverse shear, bending, and torsion, and look at their unique stress states. And finally, we'll explore material hardness, what it is, why it matters, and how it's measured. So, whether you're a student, an engineer, or just someone curious about how materials behave in the real world, you're in the right place. Let's get started. Hello and welcome back to our machine design series. Today we are talking about the mechanical behavior of materials. And as I said, we're going to get started by looking at a typical tensile test setup. In a typical tensile test setup, you'll have a tensile specimen, which typically is in the shape of what we would call a dog bone. It has a narrower center and a larger ends, and that's to ensure that we know where failure is going to occur. It's going to occur where stress is highest in that narrower center. We'll have an extensometer, potentially some load cells, and strain gauges, and then we will hook all of that instrumentation up to a data acquisition system and a computer. And on that computer, we will read out the force elongation curve. And that force elongation curve is going to tell us how our specimen is behaving under increasing load or elongation. So let's take a look at what a typical force elongation curve might look like for a ductile material. All right, so here's what our initial specimen force elongation curve might look like. And let's keep in mind what this specimen would look like. Let's give it a length of L naught and a cross-sectional area of A naught. Now, let's say that we decide to test another sample. And this sample is going to be made of the exact same material, but let's just double the gauge length so that our new specimen would look like this. Say we hold the cross-sectional area constant. We're just testing a specimen with twice the gauge length of the initial specimen. Now our force elongation curve is going to look different. And if you haven't already guessed, it's going to look a little bit flatter. And that's because this force elongation curve depends on the geometry. All right, now let's continue with this idea. Let's say we vary the cross-sectional area. Let's say that we double the cross-sectional area, but we'll hold all other parameters constant. So same material, same gauge length. Okay, we're just doubling that cross-sectional area. Now what do you think our force elongation curve is going to look like? If you guessed that it's going to have a steeper slope, you are correct. Probably looks something like this. Okay, so we've learned that our force elongation curve depends on geometry, and that means that we can't really say anything about the strength of the material just from looking at a force elongation curve. And that is why we turn to the stress-strain curve. So remember that stress is equal to force divided by the cross-sectional area, and that strain is equal to our elongation divided by gauge length. And I'll plot that in percentage. Okay, so let's take a look at what our stress-strain curve might look like for this material. All right, for all three of the specimens that we looked at, no matter the gauge length or the cross-sectional area, we're going to get the same stress-strain response. And that's because when we look at stress, we're looking at the amount of force that a material is holding over a particular cross-sectional area. So if I have let's imagine that cross-sectional area we're looking at is always going to be a 1 millimeter square. If I take a 1 millimeter square of material out of any one of these three specimens that we were looking at initially, if I take a 1 millimeter square cross-sectional area out of the center of one of those, it's going to be carrying the same load, no matter if the gauge length is doubled or the total cross-sectional area is doubled. All right, so with the stress-strain curve established, what we typically do with this stress-strain curve is we learn some things about the material. So let's label some of those things on this stress-strain curve here. All right, so first up we have point PL, and this is called the proportional limit. This is where the stress-strain curve begins to deviate from a straight line. So until then, we have a straight slope, and that slope is E, which remember is our Young's modulus of the material. So if I'm stretching a material, as long as I stay below the proportional limit, I know that my stress is going to be directly proportional to my strain. And that's why for small strains, we can use that the stress is equal to Young's modulus times the strain. Now, next up, we have point EL, and this is called the elastic limit. After this point, the material will begin to take on a permanent set. So if I load up to the elastic limit, my stress is not going to be exactly proportional to the stress, but it will still fully recover. After the elastic limit, it no longer fully recovers, but it will follow a straight line with a slope equal to E back down to the x-axis. Okay, and that point Y is called the yield point. There is a corresponding stress that you have probably heard of that we identify at the yield point. So the corresponding stress at the yield point we call the yield strength. Now keep in mind that the definition of this yield point and yield strength is sort of arbitrarily defined, although the most often definition that's used is the offset method with a 0.2% strain. All right, next up we have point U, which is the ultimate point, and SUT is the corresponding ultimate strength of the material. This ultimate strength is the maximum stress that the material can withstand. And last but not least, we have point F, which is the fracture limit. And we'll also go ahead and define that stress as SF, which is the corresponding fracture stress. All right, and before we move on, I just wanted to make one more note about Young's modulus, which is, again, this slope on the beginning section of the stress-strain curve. Young's modulus will very nearly be constant for a given type of material. So, for example, steel or aluminum or copper. Regardless of the heat treatment, carbon content, or alloying, which are all things we talked about in our previous video on materials processing, those things typically will not have much of an effect, if any at all, on Young's modulus, although they will affect things like the yield strength and the ultimate tensile strength. So keep that in mind when you're thinking about materials processing, is that you're going to typically affect the yield strength and the ultimate tensile strength, maybe the fracture strength, but you will not affect the Young's modulus much, if at all. All right, now these stress-strain curves that we've been looking at are generated typically from a tensile test. This one that we're looking at here was generated from a tensile test. And these tests apply a pulling force along the length of the specimen, producing normal stresses. That is, stresses perpendicular to the cross-section. The material properties that we've discussed, like yield strength and ultimate tensile strength, they're all typically based on these normal stresses. However, in the real world, materials often experience different types of loading, not just tension. These include bending stress, transverse shear, and torsion. So let's take a look at each of the different typical types of loading. So first up we have axial, and this is the type of loading in our typical tensile test setup. And the stress in our specimen is equal to the axial load divided by the cross-sectional area, where here I've labeled the diameter, so our cross-sectional area is going to be equal to pi times the diameter squared, not to the fourth power, over 4. And also keep in mind that this axial stress is going to be uniform across the cross-section. So if I look at a point here versus if I look at a point here or here in the center, all of those points in this section of the specimen are going to have a uniform stress distribution. They'll all be the same. So next, let's take a look at transverse shear. Now, transverse shear is what happens when a force acts parallel to the cross-sectional area. This produces shear stress, which if we were doing a stress analysis, we would want to compare to the material's shear strength, not directly compare it to its tensile strength. The distribution of transverse shear is going to be 0 on either of the ends, either the free surfaces, and it's going to be maximum in the interior of the specimen. Let me actually draw this from the side. I think it's easier to see. Okay, so the transverse shear stress is going to be small, 0 on the top and bottom surfaces, and very small near those surfaces. And then as we get closer to the center of the beam, it's going to get bigger. All right, so that's transverse shear. And if you want to learn more about these distributions and how to use this equation, VQ over IB, take a look at some of our earlier videos where we talk about stress analysis. Next up, we have bending. So in a specimen that is undergoing bending, we've got a moment or possibly a force at a distance that is applied on our part and causes the beam to bend. This introduces a gradient of normal stresses. The material on one side is in tension, so in this example, the bottom surface of our beam would be in tension because this beam wants to bend into sort of a smiley face, right? So on the top side of the smiley, we're compressing the material together. On the bottom side of the smiley, we're stretching the material apart. And to find out what the magnitude of stress is at any point along the cross-section of the beam, you can use the flexure formula, which tells you that the normal stress caused by bending is equal to the moment times y, the distance from the neutral axis, divided by I, which is your second moment of area. All right, and the last stress state we'll talk about is torsion. And I draw torsion as these double arrows, but you can think of it as like a twisting load, like what you'd see in a drive shaft or a screwdriver. And this causes shear stress throughout the cross-section, especially at the outer surfaces. So you could imagine that if we had a straight line of material here initially, after we apply this torsion, this twisting load, that line is now going to have a bit of a downward slope to it. Okay, but at the center, it's going to stay at the same center that it was at. So our torsional shear stress, tau, is going to be equal to the torque applied times rho, which is the distance from the center of the cross-sectional area, over J. All right, so understanding which type of load that you have tells us what type of stress that we're dealing with and which material property to compare it to for safe and reliable design. Now, if you have a part and you want to non-destructively understand something about the strength of the material, then one tool that you have at your disposal is hardness testing. Hardness is a material's resistance to deformation, typically from a pointed or indenter tool, and it gives us an idea of how well a material can resist scratching, denting, or wear. This is particularly important for applications like gears or bearing surfaces. Hardness testing is considered non-destructive in most cases, especially because the indentation is usually very small and it doesn't typically significantly alter the part's function. There are two common hardness tester methods. One common method is the Rockwell hardness test. In the Rockwell hardness test, a minor and then a major load are applied using a specific indenter, and the hardness number, which will be either R sub B or R sub C, is read directly from a dial. This makes Rockwell testing easy and quick to use in the lab or in a shop or even out in the field. Now, another method of hardness testing is the Brunel hardness test. This uses a hardened steel or tungsten carbide ball as the indenter, and then the hardness number that we get is HB. It's called the Brunel hardness number, and it's calculated just by dividing the applied load to the area of indentation. And this method is typically used for materials with coarse structures or rough surfaces like castings. Now, an interesting thing about the hardness number is that for many metals, there is a roughly linear relationship between the ultimate tensile strength, and the Brinell hardness numbers. This means that we can often estimate the tensile strength from a simple hardness test. This is a very useful shortcut in practice. Keep in mind that this is a correlation. It gives you an indication of the ultimate tensile strength, but it does not give you an exact number or an exact measurement. Another thing to keep in mind is if someone tells you the hardness number of a material, you need to know whether that's a Rockwell hardness or a Brinell hardness. And if it's a Rockwell hardness, you need to know, is it Rockwell B or Rockwell C? That does make a difference. Now back to the relationship between Brinell hardness and ultimate strength. I will write out that relationship. Okay, here's the relationships between Brinell hardness number and ultimate strength as given in your textbook. Now, there are two different sets of equations here. It depends on whether you have a steel or a cast iron. And remember that cast iron is just steel with more than 2% carbon in it. And so these equations, again, are rough relationships, correlations. The difference between 1.9% carbon and 2.1% carbon is not a perfect step up as we've got it outlined here. That's just a side note. But for the purposes of this class, if I tell you it's a steel, you can use this top equation. If I tell you it's cast iron, of course you can use this equation for cast iron. But just to keep in mind that a lot of the things that we use as engineers, there is some gray area, and you have to remember the assumptions that you've made all throughout your analysis to understand and be able to interpret the final result that you get at the end. So now let me just write out a couple of example questions just to make sure that we understand how to use these equations, and then we'll wrap up the video. All right, so for our first example, we've got a steel with a hardness number of 275, and we're asked to estimate the ultimate strength of the steel in megapascal. So why don't you pause the video and try that out yourself, and then come back and make sure you get the same answer as me. So the ultimate strength, we're going to use the equation for steels because we're told it's steel, and we want the answer in megapascals, so we use this bottom line of the equation. So our ultimate strength is going to be equal to 3.4 times our hardness number, which was 275. So our ultimate strength in megapascals is 3.4 times 275, 935 megapascal. Got that one? Let's try one more. All right, so for our second example, we're told that we want to design a part with a minimum ultimate strength of 20 KSI. We're asked what hardness should be specified. So first, we're not given enough information in this problem. We need to know whether this is going to be a steel part or a cast iron part. But let's say that we weren't told that, and we've got to come back to our boss with an answer. So let's just figure it out for both. We'll say if it's a steel part, and we want our ultimate strength to be equal to 20 KSI, so we're going to use the form of the equation that's written in KSI, which is the top line. Our ultimate strength needs to be 20. We set that equal to 0.5 times our hardness number. We can solve for the hardness number here and find that it is going to be 40. Now how about if it's cast iron? Again, we're going to use the top form of the equation here because we have units in kpsi. So we'll set 20 equal to 0.23 times our Brinell hardness number minus 12.5 and solve for that Brinell hardness number. So 20 plus 12.5 divided by 0.23 need to be 141. Okay, so if we were given this problem to do, we needed to report back an answer to our boss, we would say, well, if it's steel, then the hardness number, Brinell hardness number should be 40, and if it's cast iron, the Brinell hardness number should be 141. This is a pretty common practice for QA, QC, right? Let's say that I want to design a part with a particular ultimate strength. Then once I've produced a lot of those parts, I can pull one or two out of that lot and use a hardness test, which is non-destructive, so I'm not going to be damaging or ruining the merchandise that I've produced. I can use a hardness test to ensure that I meet the specification of this ultimate strength being 20 KSI. And we would probably put an extra buffer on top of this hardness number to make sure that we really do achieve a minimum ultimate strength of 20 KSI. All right, so with that, I hope that this video has been helpful. We explored hardness, we explored different types of loading, the stress-strain relationship, typical tensile test setup, and I think we're well set up to begin talking about failure theories in our upcoming videos. So I hope you're looking forward to that. Thank you for watching, and I hope to see you in the next one.